Hello students, in last lecture we have seen what is Cauchy sequence and theorem 7, that is, if sequence of real numbers is a convergent sequence, then it is Cauchy sequence. Now in this lecture we see next theorem, theorem 8, that is, if sequence Sn n is equal to 1 to infinity is Cauchy sequence of real numbers, then sequence Sn is bounded. That means if any sequence of real numbers is a Cauchy sequence, then it is always bounded sequence. So we know that if sequence is a Cauchy sequence, then by definition of Cauchy sequence, for given epsilon greater than 0, there exists a integer number, say capital N, belongs to set of integers I, such that mod Sm minus Sn is less than epsilon for mn greater than or equal to capital N. So this is definition of Cauchy sequence. I have explained in last lecture the meaning of this definition is, that means for some integer values capital N, the terms of the sequence are coming close to each other. This mod Sm minus Sn is less than epsilon for m and n greater than or equal to capital N. That means from S capital N, here m and n values are starting from capital N. So from S capital N, all the terms, the difference between all the terms is less than this epsilon, and for given epsilon, there this capital N will change. So this is by definition we have written. Now if we take value of epsilon is equal to 1, then this statement becomes mod Sm minus Sn is less than 1 m for m and n greater than or equal to capital N. That means this is, you understand that this is not for all terms, not from first term S1, S2, S3 like that, but terms from n is equal to capital N. So S capital N, S capital N plus 1, S capital N plus 2. For those terms, this mod Sm minus Sn means difference between any two terms is less than 1. Now let us take small n is equal to capital N. That means this nth term is equal to capital nth term. That means here we fix this term as S capital N. Therefore, mod this becomes mod Sm minus S capital N is less than 1, and now here n is substituted by capital N. Therefore, this is remaining m. M is greater than or equal to capital N. So, this is our statement. Write for that statement as number 1. Now, mod Sm is equal to, we can write it as adding and subtracting S capital N. So mod Sm minus Sn plus Sn. And now this modulus addition of these two terms, if we separate, then here we get less than or equal to sign. So this mod is less than or equal to mod Sm minus Sn plus mod Sn. This is result. If addition of two numbers is in modulus, and if we separate those two modulus, then this addition, modulus of addition, is always less than or equal to their separate addition. So therefore this is less than or equal to mod Sm minus Sn plus mod Sn. Therefore, now this mod Sm minus Sn is less than 1 here in equation number 1. We already written as this is less than 1. Therefore, this is less than, for this we substitute 1, and therefore this becomes mod Sm is less than or equal to 1 plus mod Sn. Now this means that this is for all m greater than or equal to capital N. That means this is for the terms starting from S capital N. That means modulus of nth term or mth term is less than 1 plus modulus of S capital N. This is for the terms from S capital modulus mod of S capital N. Next term will be mod S n plus 1. Next term will be mod S n plus 2 dash dash. So m greater than or equal to n. That means these are the terms, and for all these terms we have written mod Sm is less than or equal to 1 plus mod Sn. That means for these terms, this 1 plus mod Sn is an upper bound. Each mod Sm is less than some term. That means this term is upper bound for all mod Sm from Sn, S capital N to onwards. So for these term mod Sn, Sn plus 1, Sn plus 2 mod, and so on, for all these terms 1 plus mod Sn is an upper bound. Now the terms which are behind these terms, that means previous terms from n is equal to small n is equal to 1 to n minus 1. That means mod s1, mod s2, mod s3, mod sn minus 1. For these terms, suppose capital M is a maximum between these terms, then this mod Sm will be less than or equal to capital M for m is equal to 1, 2, 3 up to n minus 1. See, from capital N to onwards, capital S capital N, S capital N plus 1, S capital N plus 2. For these terms, 1 plus mod Sn is a upper bound, and for other terms from 1 to capital N, for those terms we have taken that maximum value of all those terms is a capital M. That means any term mod s1, mod s2, mod s3, mod sn minus 1, any value between these is less than this maximum value or equal to maximum value. Therefore, mod sm is less than or equal to capital M for m is equal to 1 to n minus 1. That means from 1 to n minus 1 terms, capital M is a upper bound, and from capital N to onwards, this 1 plus mod Sn is a upper bound. And therefore, for all the terms, we can say that mod Sm is less than this maximum value capital M plus this upper bound 1 plus mod Sn. Addition of these two will be an upper bound for every term, for every mod Sm. Thus, we have shown that this Sn sequence is bounded when mod Sm or mod Sn is less than some finite number. Then we can say that this sequence is bounded sequence. So we have shown it here. Therefore, sequence Sn is bounded sequence. Thus, if sequence is a Cauchy sequence, then it is bounded sequence. So we stop here.